So far in the lecture 2, what we have covered, we have actually started with the introduction of computer system, top level view of the computer system, processor register, instruction execution, how operating system runs the program, and interrupts. So first of all, what is the computer system? We already discussed computer system is one that actually takes input from the user, process that inputs, and give you a set of output. So any software or any system that actually takes input, process it, and gives you output, that is computer system. Second is, what is operating system? Operating system is a program that acts as an interface and control and allocate resources to other programs. We have a abstract view of the computer, whether we can see here that operating system actually communicating with CPU, RAM, and IO. That means input output devices. That means all the hardware are being communicated by operating system. Any other system software or application software, be that a game or the headphone you are listening to, suppose you are using Zoom. Even Zoom has to go through operating system for accessing input output devices like headphone or mouse and so on. Now then we have discussed the basic elements of a computer. There are 4 basic elements: processor, main memory, input output modules, and system bus. Then we have seen how this actually work properly to make sure that you run operating system and different other programs. This is basically a setup where the task of a computer is divided into 3 parts. One is IO module, that input output devices. We have a buffer. We have discussed what is the task of the buffer. Then we have the main memory, where we actually load the main memory, where we actually load all the data and instruction from the hard disk, or we can say the secondary memory. Then we have the CPU, where we actually, whenever a program is running in the CPU, you have the program counter that stores the next instruction to be executed. IR, that is stored the instruction that you are executing. Execution unit, or also known as ALU, arithmetic logic unit, actually executes instructions or executes the calculation needed to complete instruction. Then we have memory address register, memory buffer registers, IO, and IO bear. So all these actually have their own set of tasks. So whenever you are running a program, all these registers work together to actually make sure the program works properly. Then we have the system bus that actually transfer data, transfer addresses, and so on. So it makes sure that communication between CPU, main memory, and input output module are done properly. So we have data, and we have instruction. 3 things that are passed by system bus. And then we have seen what is a processor register. A processor register includes a set of registers that provides memory to the faster and smaller than the main memory. So basically, whenever we're executing a program in the CPU, we need a little bit faster memory, and processor registers are basically memories that are smaller in size but faster in speed. There are 2 functions. Regarding the function, there are 2 types: user visible register, control and status register. So there are 4 types of user visible register, as we can see. General purpose, that actually store both data and address. Then it holds temporary reserves. Then data register, that actually holds the data. Then we have address register to hold the addresses, and control conditional codes to actually that are set by the CPU hardware as a result of operations. So these are just go through them. These are very simple. Then we have control and status register. Then we have different registers and their tasks on one line. And then we have PSW, program status word, and we use all of this combinedly to make sure that the programs actually operating system runs smoothly. Then we have started with instruction execution, that we have told if a program has multiple instruction, what happens? The operating system or the CPU actually fetch instruction, it executes the instruction, and then it actually look for if there is any other instruction or not. So there I can actually add another point: any instruction left. Sorry about the handwriting. So any instruction left. So if there is any more instruction left, it actually goes back to, again, from here, it actually, if the answer is yes, it goes back here and actually again fetch another instruction and execute the instruction. And if no other instruction left, that means if the answer is no, then it actually halts the program. So these are the topics that we have discussed in the last class. So here is the diagram of how this fetch, decode, execute work. So I will now show you a simulation of this. Just wait a minute. So then the topic is how operating system runs a program. So you see, whenever you turn on your computer, okay, the first thing happens to the computer that it actually loads the operating system, whether it's a Mac or Linux or Windows 10, to your computer's main memory. So because operating system is the program that actually communicates with all the hardware. So this thing that if you don't have the operating system, you cannot even type your password to log in. So the first thing the computer needs to do is load the operating system. So first, what happens? So first is whenever you actually run the program, an example can be computer boots and begins running the operating system. And OS code must get into the memory somehow. Now, the process you have seen that this first two steps, including the number 3, the fetch, decode, and execute operating system instructions. So basically, whenever you turn on the computer boots and begins running the operating system, and operating system code actually fetched, decoded, and executed. And after the operating system is run properly, the OS actually request user input to actually run other programs. So this first 3 steps that you see here, these are actually not that simple. We will actually study these steps in details. This is actually very amazing how computer actually from zero, it starts your computer. And there's another exciting part is that previously all of us know that Windows 10, sorry, not Windows 10, Windows XP, those took almost 10 minutes to 12 minutes, 15 minutes, depending on the computer to start. That means the operating system, Windows XP or Windows Vista, took 10 minutes to be loaded into the computer. But nowadays, the whole operating system, which is much more actually efficient, and it takes only 5 seconds to load. So there are 2 reasons for that. Number 1, we have now better hardware. That means we have a better processor, better RAM, and so on. And another is that we also have a efficient algorithms to load it. So operating system actually got much more efficient. So we actually study in details how these 3 steps are done. But for now, you have to remember, whenever you turn on the computer, what happens? First, the computer loads the operating system. So it fetch, decode, and execute all the operating system instructions. And after that, when the operating system are run properly, so the kernel, the utilities, the device drivers, all the components of operating system are loaded properly, then you can see the screen and you can actually give your password. Or if you don't have a password, you can actually go to the home screen directly. So then you can actually request, you can select different applications and you can run those applications. And what the operating system does, it actually loads the application executable file into the memory. Now, what is an executable file? If you have written, it's called exe file. So if you have a game or you have a VLC player or KMP player, you will see that these are called the executable file. Or if you have done a C or C++ programming that you have done, I know. So you will see after you actually compile your program, there is a file.exe that is being created. So you can actually run the program just double clicking on that file. So every program that you have in your computer, every software, so whenever your computer turns on, operating system, actually whenever you select software, operating system load that executable file into the memory, and after loading that, it also loads the address of the application's first instruction. So basically it loads all the data related to running the application to the CPU and the main memory, and then CPU fetch, decode, and execute the application instruction, just like the last one. So this is how the operating system actually runs the program. Now, then we have another task, that is interrupt. Now, before starting the interrupt, let's go back to an easy topic first. So here, the memory hierarchy. What is a memory hierarchy? So you see, now we have seen that computer has different types of memory. First of all, we have this main memory, the hard disk, the secondary memory, the hard disk, then the main memory, then RAM, ROM. Then we have different registers, very smaller in size, but faster. Then we also have cache memory. So computer actually have different types of memory, and their characteristics are capacity, access time, and cost. That means capacity, access time, and cost. So what does this mean? That some of the memory types have high capacity, just like your hard disk, you have 1 terabyte or 500 GB of hard disk. Access time means some of the memory actually can be accessed faster. And cost means the cost per bit. So if 1 terabyte of hard disk cost around 10,000 taka, so cost per bit will be 10,000. 1 terabyte equals to 1 into 1024 into 1024 and dot 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 bit, and divided by 10,000. So cost per bit. Then, in short, the faster the access time, the greater the cost per bit. That means if you want to fast memory, you need to spend more amount of money. If you want a greater capacity, then the cost will be less. Okay, and if you want a greater capacity, it will be slow. So that is the problem with the hard disk, that even though it has a great capacity, it's actually, and it's also cheap. Okay, so we obviously want to use that, but problem is it's slow. So computer CPU actually needs a faster memory system. Okay, so what is a faster memory system? So we can see that we have the cache memory, we have the RAM, that is the main memory, and so on. And this is actually a diagram whether we can see that, you see, at the lower we have the magnetic tape, the hard disk, and then we have the DVD-ROM, CD-ROM, magnetic disk, and then we have the main memory, that is, let's assume RAM, then we have the cache memory, then we have the registers. So the fastest memory, if we go up, okay, more expensive, faster, and smaller. That means magnetic disk. From magnetic disk we have fast CD-ROM, DVD-ROM, these are actually faster. Sorry, I have from magnetic tape, the magnetic disk is faster, but more expensive and smaller. From magnetic disk to we have the main memory, which is actually more expensive, faster, and smaller. And then we have the cache memory, more expensive, faster, and smaller, and so on. And as you can see, these are divided into 3 layers. Okay, the first layer is offline storage. Okay, that is our magnetic tape. Then we have the outboard storage, that is our magnetic disk, CD-ROM, CD, and DVD write, and DVD RAM. Then we have the inboard storage inside the computer, adjusted with the processor, motherboard. We have registers, we have cache, we have main memory. And if you go down, it becomes slow, but the size actually increases and cost also decreases. So that's how the memory hierarchy works. It's easy to remember. Okay, the higher the size, okay, the slower the speed and the cheaper it gets. And the faster you want, the more money you have to spend. Then we have the cache memory. So let's start about the memory cache. So first of all, let us see why we actually need the memory cache. So I have already discussed that we need actually cache memory because that our CPU actually works very fast, but the problem is the other storage that we have, the main memory and the secondary storage, they are actually not that fast. One example can be that if the CPU can execute 100 instructions per second, what does this mean? This means that you have to load 100 instructions from the main memory to the CPU so that it can execute it. But now you see, suddenly you notice that even though your CPU can actually execute 100 instructions per second, your main memory can actually only transfer 50 or 20 instructions per second. So what will happen? Your CPU will actually sit idle because it doesn't have any task at hand. So we actually don't want that. We want to make sure that our CPU usage is as efficient as possible. Now, processor speed is much faster than the memory speed. Okay, that's the first point. Hence, increase the speed of memory is necessary. So as I have said that we need to make sure that the memory speed is fast so that it can keep up with the CPU. And memory cache contains a portion of the main memory. So what cache does, it actually contains a portion of the main memory where data is stored there. So whenever CPU asks, instead of directly going to the main memory, okay, the cache actually supplies the data. So basically it's like a copy version. Okay, but because cache is a little bit faster, it actually can deliver faster. Processor first check the cache for required instruction. So if the instructions are there, it doesn't go to the main memory. But if the instruction is not there, it goes to the main memory. So here, as you can see on a picture, so we have the CPU here, we have the main memory here. So normally whenever the CPU needs the instruction, it comes to the main memory directly. But the problem is, as I have said, the main memory is slow. So we can say that even though CPU wants 100 instruction per second, the main memory can only supply 50 or 20 instruction per second. And that's why you have the cache memory. So what the cache does, it actually keeps a copy of the main memory, a portion of the main memory. It cannot copy the full main memory. So whenever CPU actually wants the instructions, cache actually provides it. So it becomes a little bit faster. Now, how the read operation work, I will discuss it later. Let's first go to the key elements of cache. So what we need in a cache, first of all, cache size. Okay, so first of all, we need caches to be small because they have the significant impact on the performance. Why? Because the slower, as we have told, the smaller the memory, the faster it becomes. And then the block size. Okay, what is a block size? Is basically here, as you can see, block transfer. So in the main memory, we have actually boxes like this. We have seen, let me draw the box. So we have a box like this, and we actually divide it into some smaller boxes. So we can actually, for now, we can actually call them block. So what will be the block size of the cache? Because unit of data exchange between cache and the main memory. So will you transfer 1 megabyte or 20 block or 32 bit? Like what will be the unit? That is actually you have to decide unit of data. And block size increases very small to larger sizes. So basically it's normal, right? If you want to transfer more data, we have to actually increase the block size. Then we have to talk about the mapping function. What is the mapping function? So let's assume this is my cache memory C, and this is my main memory M. So this is my main memory. Now, let's assume in my CPU, currently there are 5 programs. Okay, this is program number 1, this is program number 2, and so on. Okay, so now if I'm actually running the program number 1, or I can say if I'm executing the instructions of program number 1, so if this is the data of program number 1 and this is the data of program number 2, so which actually needs to be loaded into the cache? Obviously, we can all agree that if these data in this area, we have the data of program number 1 or instructions of program number 1, we have to load or map this part of the main memory to the cache memory. So when a new block of data is read into the cache, it determines which cache location the block will occupy. So if you read a data, it will make sure that yes, it should go here or it should go here in this part. So even though the picture doesn't make it clear, don't worry, we'll actually discuss cache more in the later lectures. So for now, then we have the replacement algorithm. We'll also study this replacement algorithm, and they are actually very important. Even though, if you want to, whenever you go for any interview or any master's exam, I have seen that these questions are very common from operating system. Like they will give you a question of how this replacement recently used LRU algorithm work or some other replacement algorithm work. So we'll study about these algorithms, and then finally we'll study about the write policy. So how you can actually write a block of cache back to the main memory. So suppose one part of the task is done, how you can actually transfer it back. And one point, main memory must be current for direct memory access, IO modules, and multiple processor. So what is direct memory access and IO modules? We'll discuss it from the next slide. So let's just summarize here. So we have in memory hierarchy, we have 3 characteristics: capacity, access time, and cost. We know the faster access time, the cost is more. The greater the capacity, the cost is less. The greater the capacity, speed is also slow. Then we have the hierarchy here. We have seen that we can divide into inboard memory, outboard storage, and offline storage. And then we have seen the memory cache is actually used for so that CPU can actually, the CPU can actually work more efficiently, and processor speed is actually much faster than the memory speed. And then we have seen that how actually this work. Now, after that, we have seen the key elements of cache design: cache size, block size, mapping function, replacement algorithm, and write policy. So these are the 5 points we need to consider in cache. Now let's see how actually read operation work. So first of all, you start the program and receive an address of RA from CPU. So RA means read address, as you can see here. So basically the CPU tells me that read me from this portion of the memory. So let's assume you want to play a game. The name of the game is House of the Dead. Okay, and the House of the Dead, the game is actually stored into the sector 1 of your hard disk. So the CPU will tell us that give me the read address of sector 1. So it will actually receive the address from the CPU. That means cache will have this address. Now, first, what the cache will do, it will actually check whether this address is actually already in my block or not. That means whether I already have that instruction or the data from this address. Okay, so if you already have the data, yes, then it actually fetch the word. That means from that read address, suppose if the address is sector 1, from sector 1, it will fetch the data and deliver it to the CPU. Okay. And then it will be done. And but if the block is not in the cache, what it will do, it will first access the main memory for that block containing that read address, allocate cache to slot for the main memory. So that means, okay, now I have pointed out that I don't have this memory. So what I will do, I will first go to the main memory, that okay, give me this data or instruction from this address. And at the same time, what I will do, I will actually allocate my slot, because I am a cache and I don't have unlimited space. So I will actually allocate space for those data that will be sent from the main memory. And then I will actually load main memory block into cache slot. And so I will load those data into my cache and deliver array word to CPU. That means read address word, the data to the, or the instruction to the CPU. Then I am done. So basically 2 steps. First, I will receive address from the CPU. CPU will tell me that read me those data. Then I will ask that whether the data is already here. Okay, this can be data, it can be instruction. If it's already here, I will fetch and deliver it to CPU. If it's not here, I will go to the main memory. I will find that data, and at the same time, I will actually allocate space in my cache to actually store that data. And after receiving the data from the main memory, I will actually load them into my memory block or cache slot and also deliver it to the CPU. So that's how actually cache read operation work. Now, another easy topic for today's class, that is IO communication technique. So IO communication technique, first of all, we have to understand what is IO communication. IO communication means input-output communication. So what is the reason for IO communication? It can be different reason. For example, if you want to actually store a data to your hard disk, or you want to actually delete some data from the hard disk, or you want to show something from your hard disk. Okay, so basically whenever you need to do any input or output operation, okay, so we need to use this IO communication technique. So what it does, so when the processor executing a program and encounters an instruction relating to IO. So basically now the problem is, so okay, you need to load data, or you need to write data, or you need to do IO communication. But suppose your processor is actually busy doing other tasks, okay, other important tasks. Okay, so now you want to actually, don't want your processor to get disturbed, okay, but at the same time you want to do the IO communication. Is there any better technique? So let's first go through the slide, then I will explain furthermore. So it executes that instruction by issuing a command to the appropriate IO module. So if you need to take input something, okay, so suppose if you need to take input from the keyboard, so your processor will actually issue a command, okay, or instruction to the appropriate IO. That means the input output module, that is, so let's assume keyboard. There are 3 techniques: programmed IO, interrupt driven IO, and direct memory access. Now let's try to understand this cycle. So what happens, that CPU actually understands suddenly that, okay, I need to take some input. So CPU actually goes from the cycle 1 and cycle 2, it goes on like this. So CPU to memory, memory to IO, and IO to back to CPU. So let's see what this actually means. So first of all, programmed IO. So I will first give you a simpler example, okay? So let's assume that all of you have done the course registration. Okay, so here we have 40 students in this class, and let's assume of all the 40 students, you actually need to do the course registration. So the rules in IOBT for course registration is that you have to go to the department and registration will be done by Utpal sir. Now, let's see what will happen, that you will go to the department, okay, you will sit before Utpal sir, you will actually register yourself, and then you will come back. So they're very simple, right? But the problem is, suppose you went to Utpal sir, okay, and then suddenly you actually need some more information for your registration to complete. Okay, so then the Utpal sir said, okay, don't worry, go, wait here, wait here, finish it. So you sit in front of Utpal sir, you actually finish your application, and then you actually come back. Now you see the problem here, that when you actually were finishing the registration, what happened, that Utpal sir was the whole time he was sitting there idle. Okay, he was not doing anything. So just think of the CPU. You want to take some data from one of from the input out from the memory, and then if your CPU is sitting idle for the whole time, it's actually not efficient. So another better approach can be, okay, then what I will do, I'll actually go to Utpal sir and I will try to do my course registration. And if I have some data missing, okay, what will happen? I will actually, Utpal sir will say, okay, Sakib, you have some data missing, go collect those data. And meantime, what Utpal sir will do, he will do the registration for the next person. So when my data is ready, okay, I will come back and then I will finish my registration. So what is the difference between these two methods I have just told? In the first one, it was that I was actually, I went there, I finished the whole task, and then I come back. Okay, and the whole time Utpal sir was with me. Okay, he didn't actually do any other task. So he actually, his time was wasted. And next, in the second one, what happened that while I was actually looking for data to fill up the data, Utpal sir was explaining this to another student. So in that case, what happened that as Utpal sir was explaining to another student, it actually became more faster because you are writing and meantime Utpal sir was doing some other task. So this is another case. Okay. And third case is that Utpal sir will not be involved that much at all. Will actually involve the department AO. Let's assume Polash Bhaiya. So what will happen? You will go to the course registration. You will just take one thing. You will take the permission that Utpal sir, can I do the registration? Utpal sir will just say yes. And rest of the tasks will be done using with Polash Bhaiya. So in that case, you see Utpal sir, if I compare it to the CPU, it was actually free most time. Okay, he can actually give permission to 50 people now because rest of the task is being done by another person. So now this whole time, okay, the CPU is actually free and it can do other tasks. So this is the three cases. Now programmed IO is the first case where Utpal sir does your registration, and if you have any problem, you sit there and solve it. So Utpal sir actually cannot do other work. In interrupt driven IO, what happens that whenever you actually have any problem, you actually go back, you collect the data, meantime Utpal sir actually help other student. So in that case, you actually Utpal sir actually can do some more tasks. Okay, he doesn't sit idle for that much. And in direct memory access, what happens that Utpal sir actually just gives you permission and you actually finish the rest of the task with Polash Bhai or any other AO. So it actually, in case of CPU, this one is good, but this one is much better and this one is the most efficient because here Utpal sir is free, because here the Utpal sir is free more time. Okay, so that's how DMA work. Now we will see how it actually works, but let's take 2 minutes. There is a Ajan going on, so let's take a break. Okay, so as I was saying that first of all, we'll discuss the programmed IO. So first of all, how programmed IO work? Let's first go through this 4-point. Input output module performs the action, not the processor. So input output module will take the input or the output and so on, sets appropriate bits into IO status register. So what does this mean? So whether to actually the input was taken properly or how to take input, all this actually have some conditional flags. So those are actually set by the IO status register. And then no interrupt occurs. What is interrupt? We'll also discuss in some later slides. And then processor is kept busy checking the status. So this is the actually important part that you have to understand, that while we are taking programmed IO, that means we're actually using input output module to perform the action. Okay, still we are keeping the processor busy. That means CPU, even though it's not taking the input, that input is taken by the mouse, the keyboard. Okay, the IO module, we're actually keeping the CPU busy all the time. So let's see how we're actually keeping it busy. So first of all, you see, issue read command to the IO module. So CPU actually sends command to IO module like keyboard, mouse, or controllers that take input. Then what the IO module does, it actually reads status of the module and send it to the CPU. So if it's ready, the status is being checked whether it's ready or not. Okay, if it's ready, we actually proceed to the next step. If it's not ready, we actually again go to the previous step. From not ready, we'll go back here. So it again reads status of the IO module and it actually checks whether it's ready or not. Now the question is why it will not be ready. Okay, why my keyboard will not be ready? So sometimes it might happen your keyboard is not working or it's actually doing some other work. Okay, your IO module is doing some other work. In that case, it will not be ready. So your IO module will check whether it's ready or not. Okay, and it will let the CPU know. So CPU will check the status. Okay, and processor will kept busy checking the status. That means this is one of the tasks that actually keeps the CPU busy. So even though you are doing the course enrollment on your own, okay, Utpal sir has to check whether everything is correct or not. And that's why he is being kept busy. Okay, and then if it's ready, it actually reads what from the IO module. That means it actually takes the input, and that input is being sent to the CPU, and then the CPU actually sends the input to the memory. And then if we are done, then we actually go to the next instruction, and if we're not done, we actually again issue another command. So again, let me summarize. So first, CPU actually gives that, okay, give this input. Okay, I need this input from this IO module. IO module check whether it's free or not, or ready or not. If it's ready, it let the CPU know that yes, my status is ready. Okay, so what the CPU does, it takes input, sorry, the IO module takes input and send it to the CPU, and then CPU actually sends it to the memory, and then we check whether we are done or not. So if I compare with the course registration process, okay, so first Utpal sir asks you to fill up this form. You actually see whether you have all the data. If you have all the data, you actually start filling up the form. If you don't have all the data, you actually again keep collecting the data. And all this time, Utpal sir is sitting in front of you idle. Okay, the CPU is just waiting. Then if you have all the data, you actually collect all the data and send it to the CPU. That means you send it, give it the data to Utpal sir, then Utpal sir finally store the data or do your registration. So basically that's how the CPU is being kept busy all the time, even though CPU doesn't have much more tasks. So this is called programmed IO. And here is one unknown term, that is interrupt, and another term that is called IO status register. So we'll discuss this, don't worry. Now let's go for interrupt driven IO. So what happens here, let's first read this. So processor is interrupted when IO module ready to exchange data. Processor is free to do other work, no needless waiting, consumes a lot of processor time because every word read or written passes through the processor. Okay, so let's explain one by one. First of all, processor is interrupted when IO module ready to exchange data. So let's come to this picture. What happens? Again, issue read command to IO module. So CPU actually reads command to the IO module. Same as the last one, you see, CPU to IO module. But after that, what happens, that CPU actually, just after telling you to fill up this data, okay, let's suppose I'm the student, so he will, Utpal sir will just fill up this data, and Utpal sir will go to another student. Okay, so it's up to you now, fill up the data. So when the data is ready, okay, you have seen that, okay sir, I have all this data. You will let Utpal sir know, sir, I have all this data. Previously what happened, Utpal sir was waiting in front of you, okay, but now Utpal sir, meanwhile Utpal sir is doing actually something else. Okay, maybe he's talking to someone else or helping other students, and then it will, IO device will know, CPU know, and then if it's ready, then it will go, IO will send it to the CPU and CPU will send it to the memory. The rest of the steps are same. The improvement was in this step. That means now Utpal sir is not waiting for you. Okay, he will do some other task, and meanwhile, whenever you are ready, you will let Utpal sir know that, sir, I have all the data ready. So now let's go back here. So how this is better? So processor is free to do other work. No needless waiting. So processor doesn't have to wait for you. Consumes a lot of processor time because every word read or written passes through the processor. So again, the same problem. This actually pointing to this area. So whenever you are reading a data, okay, first you have to send it to the CPU, and CPU has to send it to the memory. So this is the problem in the interrupt driven IO. Now, what is the better? So then we have direct memory access, DMA. So before understanding the DMA, we have some commands. Okay, so let's here first start slide by slide. Device has to send DMA request. Okay, DMA queue, that is named DMA queue, to the DMA controller. So okay, we have to know what is the DMA controller. Second, DMA controller send hold request HLD queue to CPU and waits for the CPU to send hold acknowledgement HLDA. So okay, we are seeing some new commands so far. One is DMA request, DMA queue. Then we have the hold request, HLD queue. Don't worry, I will explain them one by one. So let's first see that what the CPU tells the DMA controller. So step one, whether it will be a read or write operation. The address of device to transfer the data, starting address of the memory, and amount of data. So instead of reading the slide, let's go to the diagram first. Okay, so peripherals here means IO, input output devices. Okay, so IO module. So what happens? So you want to write some data to the memory. So you have, this is my IO device and this is my memory. So previously what happened? First, peripherals actually send data to the CPU, and from the CPU, the data is being transferred to the memory. This was the previous case, okay? But now what we will do, instead of following this, keeping the CPU busy, we actually introduce a new concept that is called DMA controller. DMA means direct memory access. Why it is called direct? Because we are now actually not involving CPU. Okay, so we can say direct course registration. Okay, so what it will do first, it will actually send, this is step number one, DMA queue. So what is DMA queue? Let's go back. We have seen DMA queue means DMA request. That means the input output module, it will send a request that I want to transfer some data from my input output device, that is, let's assume keyboard, to the memory. DMA controller will take the request and it will transfer hold request HLDQ to the CPU. That means this is HLDQ. This request will be sent from the DMA queue to the CPU. So why this request will be sent? Because even though your course offering is not done by Utpal sir, you actually needs the permission of Utpal sir. So this is actually that way that CPU will actually give the permission to the DMA controller that, okay, you can transfer this data from input output module to the main memory. So it will give the permission to the DMA controller using HLDA. Okay. So here HLDA means we have hold acknowledgement that yes, you can actually transfer it. And with that, CPU will give some more information that whether it will be a read operation or write operation, whether you will actually read from computer memory or you will write some data on the computer memory. Secondly, the address of the device to transfer data from and to. So that means from the address of this device, whether you are sending it from a keyboard or mouse. Number three, the starting address of the memory block of the transfer. So we know we have a huge memory and CPU will specifically notify you from where you need to store the data and the amount of data. So all the informations will be given by Utpal sir, which course you need to do, okay, what is the number of credit you can take, and what is the other information you need. This will be given by the CPU or the, let's assume in our registration case, Utpal sir. And after that, this have the permission, the memory will actually start transferring the data. Now, what happens whenever this starts, peripheral actually transfer data to the DMA controller and DMA controller to memory. So now they are actually working on their own and CPU is actually free. So what is the advantage? CPU leaves the control over the bus and acknowledge HLDA signal to DMA. So that means CPU gives, okay, you guys can do it, and performs transfer while CPU does other processing. So this is the important part. While DMA actually transfer data, CPU does other tasks. And DMA sends interrupt when it's complete. So when a registration is complete, okay, let's assume your course, you actually go and told Utpal sir, my registration is done. So just give or submit him the information. Now, what is the advantage? First of all, it is efficient. So CPU can do other tasks. It is designed by Intel to transfer data at the faster rate. Okay, so easily you can transfer data and in a faster rate, and it allows device to transfer data directly to from memory without CPU involvement. So basically the same thing again and again, we can actually transfer data in a faster way.